Hyeon-yeong, and I'm the first year master's student, and I'm going to talk about the advancement in magnetic materials for high frequency applications, including like RF cores for high frequency transistors. So first, I'm going to look through the benefits and challenges of operating in high frequency and go through the magnetic materials that are used. And I'm going to talk about the further developments of magnetic materials that are going on. First of all, one of the main benefits of operating in high frequency is that we can get the reduced volume and weight. As you can see from this equation, as the transformer operating frequency increases, the size of each components, which are presented as the area, can be reduced without increasing the current density or the magnetic core flux density. So from this, we can use in applications even when there are volume and weight restrictions or it requires high control dynamics, such as traction equipment for high-speed trains or renewable energy or smart distribution grids. So recently there are many research going on using the solid state transformers, which uses medium or high frequency transistors for its DC-DC converter is widely used as a key building block. However, there are challenges of operating in high frequency. The main challenge is that we get increased loss. The reason for the increased loss can be due to the eddy current loss. So what is the eddy current is that the eddy currents are induced to oppose the flux created in the windings by the AC current, which can be seen in the Lenz's law or Faraday's law. So the eddy current cancels the current in the center and increases the current near the surface. So due to this eddy current, we can get the this current distribution, which is also called as skin effect. So the skin depth that the current goes through the conductor gets smaller as the frequency increases. So we get the increased resistance and heating, which cause the increased AC loss. Also, there are other challenges such as evaluating the magnetic materials. As we saw in the previous slide, in the high frequency environments, we get eddy current loss, skin effect, or proximity effect, and so on. So the magnetic design is now dominated by the core loss rather than the saturation considerations. This gives the challenge for evaluating, such as the performance factor. This is a very popular used factor to notify what the best frequency is for such magnetic materials. So the conventional performance factor assumes that the winding loss is independent of the frequency, which is not true in the high frequency range. So therefore, in order to operate in high frequency, we need to get the proper understanding on the trade-off between the reduced size and increased loss. And also we need to also consider the magnetic material selection, which can be quite different from medium or low frequencies. So from now on, I'm going to talk about the magnetic materials that could be used for high frequency operation. Traditionally, like in line frequency transformers, iron silicon alloys were commonly used. However, in high frequency environments, the core loss becomes prominent as the frequency increases. So to date, ceramic ferrites have been the most commonly used magnetic cores, but which can achieve the relatively low core loss. and have a lower cost to implement it. However, it also have problems that saturates at a much lower magnetic flux density level and have some impairment from ferrite cores, which also means that it is prone to mechanical breakage. So these days, soft magnetic materials are considered as a great materials for operating in high frequency. So these are the desired characteristics, which the properties is also seen in throughout our courses. So, and these soft magnetic materials can be divided in four. Traditional ferromagnetic alloys, soft ferrites, amorphous alloys, and nanocrystalline alloys. First of all, for the traditional ferromagnetic alloys, such as like iron silicon alloys I mentioned before, as you can see, the iron silicon alloys have a high saturation flux density and at high Curie temperature, but it has a very low resistivity, so that the iron silicon alloys are now usually used in applications less than 1 kilohertz. For the soft ferrites, the main property for the soft ferrites is that it has very high resistivity, which enables to have a reduced eddy current loss. However, these soft ferrites have a very low saturation flux density compared to other SMMs and have lower Curie temperature. Next, I'm going to talk about the amorphous alloys, which means it is a class of metallic materials that are not crystalline in nature as compared to most metals. This is because it is made by rapidly quenching the molten metal so that it forms a thin ribbon as a result. So for the amorphous alloys, it has a relatively high saturation flux density, Curie temperature, and permeability related compared to the soft ferrites. Lastly, the nanocrystalline alloys, nano is because it has an average of diameter about 10 nanometers. So these are the kind of nanocrystalline alloys that are made, and it tends to have a high saturation flux density, low magnetostriction, and high permeability and low porosity, which therefore makes it to have a low loss. Also, as you can see from the Curie temperature, it also shows the stable temperature characteristics, which means it can be used as a stable parameters. So lastly, I'm going to compare the important core loss between the SMMs. So as you can see from this diagram, the iron silicon alloys have the largest loss, this one. And the soft ferrites have the smallest at the lower magnetic flux density here. And the nanocrystalline have the smallest loss at the higher magnetic flux density. By comparing the other magnetic properties we've seen before, we can assume that the iron silicon alloys have the largest loss because it has a very low resistivity, which makes it to have the large eddy current loss. Also, soft ferrites has a very highest resistivity, which makes it to have a smallest loss. But because it has low saturation flux density, it had only been done at the lower magnetic flux density. Lastly, since the nanocrystalline has the overall best parameters for operating in high frequency, it had the smallest loss at the highest magnetic flux density. Next, I'm going to talk about the further development on magnetic materials. And first of all, there could be an advancement in nanocrystalline alloys. So the nanocrystalline alloys are done by melt spinning process, which means it goes in like quenching. It goes to non-equivalent metastable state to the stable crystalline phases by the glass formation ability. So in the paper I referred to said that by adding some of elements, the filament composition can get a better glass formation ability, such as substituting the cobalt with the iron. Also, there are other research that uses other magnetic materials such as gallium nitride, which shows the highest performance in high frequency operations such as military radar right now. It also has some drawbacks, such as it has the resistance depends on the voltage they use. So there are also been recent studies about using the gallium nitride with the original silicon-based transistors. Yeah, so in this presentation, I looked through the benefits and challenges in the high frequency and how the developments on magnetic materials have been done. Yeah, that's all. Thank you.